Okay, guys, this session will cover the topic of continuity. We'll discuss continuity. And then after that, is going to be the topic of differentiation, because we need continuity for derivatives as well. Okay, so let me write here continuity. Okay, so we're not going to go too deep on continuity. Let me go back. We're not going to go too deep. We're just going to cover enough. Well, as I said before, on limits in general, because continuity is part of limits. So yeah, on continuity in general, we're not going to go too much, go too deep with it, because we just need it for differentiation. We're just going to facilitate the knowledge that we need for the introduction to derivatives. Okay, so let's look at continuity. Let's look at continuity. Continuity. What is that about? Continuity. Okay, so first of all, we'll start with an example. Let's start off with an example. Okay, let's do an example. Okay, say that you want to find the derivative, not the derivative, the limit, sorry. You want to calculate the limit of a function. And suppose that your function is x squared, for example. So let f of x be equal to x squared. Okay, so that's your function. And you want to calculate the limit of this function x squared. What is the limit of x squared? When x approaches 1, for example. Okay, what's the limit of x squared when x approaches 1? Okay, so now this is the total limit, obviously. It's the total limit. What's the limit of x squared when x approaches 1? Now, as we discussed in the previous lecture, calculate this. You may use a table. You may use a table to calculate this. So to calculate this, you may use a table if you want. But I want you to notice something. First, if you do use a table to calculate this limit, you'll find that you get the answer of 1. So the limit of x squared when x approaches 1 is equal to 1. Okay, if you use a table. But then I want you to notice that if you substitute 1 into x squared, okay, if you substitute 1 into x squared, if you go f of 1, what is that equal to? That equal to 1 squared, which is equal to 1. So the limit of x squared when x approaches 1 is 1, which is the same as 1 squared. It's the same as if you substituted 1 into the function. So it's basically the same as if you did this. It's 1 squared, which gives you 1. Okay, so when a function does this, or when a function satisfies this, we say that the function is continuous at 1. If the limit of the function when x approaches a number, in this case 1, if to find the limit, we can simply just substitute into the function the number that the x values are approaching, then that function is called continuous at that number that x values are approaching, meaning that this implies that x squared, it implies that x squared is continuous at 1. X squared is continuous. X squared is continuous at 1, or at x is equal to 1. Because to get the limit, you can simply just substitute the number that the x values are approaching into the function to get the limit. So therefore, this function x squared is continuous at x is equal to 1. So that's continuity, basically. That's basically what continuity is. It's if when you find the limit of a function, you find that the limit is just equal to, or to get the limit, you simply just substitute the number that the x values are approaching into the function. A function that satisfies that is called continuous at that number that the x values are approaching. So in this case, x squared is continuous at x is equal to 1. So that's continuity in a nutshell. Okay, so it can save you time because you don't have to use a table. So if a function is continuous at the number, then you don't have to use a table. You just simply just substitute to get your limit. Okay. Again, let's suppose now that our function is suppose that we have a sine x, for example. Suppose that we have sine x. What is the limit of sine x when x values are approaching pi over 2, for example? What's the limit of sine x when x is approaching pi over 2? Okay, again, for this function here, if you use a table to calculate this limit, you'll find that this limit is equal to 1. It's equal to 1. Okay, the limit of sine x when x is approaching pi over 2 is 1. And you also, if you go and you substitute, if you go substitute pi over 2 into the sine function, you find that sine of pi over 2 is equal to 1. So therefore, again, in this case, the limit of the function, you can basically find the limit of the function when x is approaching pi over 2 by substituting the pi over 2 into the function, and which is 1 in this case. So this function is also continuous in this case, it's continuous at pi over 2 because the x values are approaching pi over 2. So this implies that sine x is continuous at pi over 2. So sine x is continuous. Sine x is, sorry, let me just go back there. Sine x is continuous. Sine x is continuous. Okay, this continuous is a bit shady. Let me just rewrite it. Continuous. Sine x is continuous at x is equal to pi over 2. So that's continuity. Okay, that's continuity. Now, in general, okay, in general, we can state the following. In general, we can state the following. So in general, we can state the following. If the limit of f of x, or we can say that f of x is continuous at x is equal to a, okay, we can say a function, we can say a function f of x, we can say a function f of x is continuous. A function f of x is continuous at x is equal to a if okay, so as I was saying, let me just go back to what I was saying. I'll erase this. Okay, so as I was saying, now in general, okay, what you can do in general, what you can say in general is this. if a function f of x is continuous at x is equal to a if the limit of this function f of x when x approaches a is equal to f of a. Okay, so a function f of x is continuous at x is a if the limit of this function f of x when x approaches a is equal to f of a. A function f of x is continuous at x is equal to a if the limit of this function f of x when x approaches a is equal to f of a. That's the general statement. A function f of x is continuous at x is equal to a if the limit of this function f of x when x approaches a is equal to f of a. Okay, so that's what continuity is. All right. Now, so as I said before, this saves you time because now you don't have to use the table. So if you're dealing with a continuous function, to get the limit, all you have to do is substitute. All you have to do is substitute. So it saves you time. All right. But then you also have to understand that not all functions are continuous. Some functions are not continuous. So you have to understand that not all functions are continuous. Okay, so as I was saying, guys, not all functions are continuous. So you can't apply this to all functions, okay? So now it helps to know which functions are continuous, like which types of functions are continuous, so that you know when to apply this. So I'm gonna write on a list, okay? I'll write on a list here of continuous functions. So you know that when you're dealing with those functions, you're dealing with continuous functions, okay? So let me write on a list. Let me write on a list of continuous functions. Continuous functions. Write on a list of continuous functions. Number one, polynomial functions are continuous. Okay, polynomial or polynomials. Okay. Also rational functions. Now, rational functions are basically fractions of polynomials. A polynomial over a polynomial. That's a rational function. So polynomial functions are continuous. Rational functions are continuous. Also, exponential functions are continuous. Exponential functions. Okay, exponential functions. Exponential functions, logarithmic functions, logarithmic functions, logarithmic functions. Okay, also trigonometric functions, let's go back. Trigonometric functions are continuous. Also, the inverse trigonometric functions are continuous. So trigonometric functions are continuous. Inverse trigonometric functions are continuous. Inverse trigonometric. Okay. Inverse trigonometric functions are continuous. Also, root functions. Root functions are continuous. Also, root functions are continuous. Okay. I could also add algebraic functions. Algebraic functions is basically a combination of all these functions here. So if you have a combination of any of these functions here, that's an algebraic function. So also those ones tend to be continuous. And these functions, of course, are continuous in their domains. Okay, so these functions here are continuous in their domains, meaning that they have to be defined at the number for them to be continuous at the number. If they are undefined at the number, they cannot be continuous at that number. So they have to be defined at the number. They have to be defined at the number. Okay, so they have to be defined at the number in order for them to be continuous at the number. So this is a list of continuous functions, but remember that these functions are continuous in their domains, meaning that they are continuous where they are defined. Okay, now let's look at examples now. Okay, let's look at examples. Let's look at examples. Let's look at examples. Okay, we're going to calculate some limits. All right. Okay, we're going to calculate some limits here. Let's look at the limit of the following. So let's start with we're going to start with a rational function. All right. Start with the rational function. Okay. Two x squared plus x plus 1 divided by x plus 3. And we're finding the limit of this. We're finding the limit of this when x is approaching 1. What's the limit of this when x is approaching 1? What is the limit of this function here when x is approaching 1? All right. Now, it's simple. This function here is a rational function because it's a polynomial over another polynomial. So therefore, that makes it rational. Now, is this function defined at 1? Yes, it is, because if you substitute 1 into the function, there's no, if you substitute 1 into this function, it doesn't give an error. So therefore, it's defined there. So therefore, 1 is part of the domain of this rational function. Okay, because the function is defined at 1. So therefore, 1 is in the domain of this rational function. So therefore, this rational function is continuous at 1, because rational functions are in that list. They are in that list of functions that are continuous in their domains. So therefore, to find this limit is very simple. It's a simple matter now. All you do is you substitute the 1 into the function to find the limit. There's no need to go and do a thing. There's no need to go and do a table. There's no need to use a table here. All you do, substitute the 1 into the function, and you've got the solution. So now this will give you a 2 plus 1 plus 1. So that's basically just 4. And this is basically a 4 over a 4. So it's 4 divided by 4. Well, there's 4 at the top. Okay, because it's 2 plus 2 at the top. And at the bottom is 4 because it's 1 plus 3. So therefore, it's just equal to 1. So the limit of this rational function as x approaches 1 is simply just equal to 1. It's simply just equal to 1. Okay, so that's what it is. So therefore now, let's look at the next example. Let's look at the next example. Next example, we're going to choose, let's say we have an exponential function. We've got e to the power of x. We'll find in the limit of this exponential function when x is approaching 0. Now, is the exponential function defined at 1? If you substitute, I'm sorry, 0, because x is now approaching 0. So the x values are approaching 0. Now, if you substitute 0, can you is the exponential function here, is it defined at 0? Is the exponential function here defined at 0? Is the exponential function here defined at 0? That's the question. If you substitute 0 in the exponential function here, it doesn't give you an error, it gives you 1. So therefore, it's not, undefined there. It's defined there. So 0 is part of the domain of this exponential function. In fact, this exponential function is defined everywhere on the real line. So therefore, to find the limit of this exponential function, all you do is you substitute the 0 into the function. This function is continuous in its domain. It's in that list. It's an exponential function, so therefore it's in that list. So it's continuous in its domain. So to find the limit of this, all you do is you substitute 0 in there, and you get yourself a 1. So again, another limit, which is 1. Okay, not all the limits are 1, obviously, but these functions we're looking at, it so happens that the limits are 1. So now let's look at another example. Let's look at another example. Let's look at an example where we have a logarithmic function. Okay, let's look at a situation where we have a combination of maybe a log function and another function, because also those ones are also continuous in the domain. Okay, if you, as I said, if you have any combination of these functions on that list, okay, if you have any combination of these functions on that list, by combination meaning that, okay, you're adding them, you're subtracting them, or it's a composition of them, meaning that it's one in the domain of the other. Those functions, which are combinations of all these functions, of any of these functions, will also be continuous in their domains. We call them algebraic functions. So let's go here to number 3. All right, now going to number 3, look at another example. Let's look at the example where we find the limit of ln. Let's say we've got ln. Okay, let's say it's ln of sine of something. Okay, suppose it's ln of sine of something. So let's say it's ln of sine of t. Let's use a different variable. Okay, let's say it's ln of sine t, and t is approaching some number. Okay, ln of sine t, and t is approaching a number. Let's say t is approaching power 2. Okay, what happens when t is approaching power 2? Okay, so we find the limit of ln of sine of t when t is approaching power over 2. We find the limit of ln of sine of t when t is approaching power over 2. Again, is this function continuous in its domain? Yes, it is, because it's a combination of those functions. It's a combination of the functions on that list of a log function and a trig function. So it is continuous in its domain. But the question is pi over 2 in the domain of this function? Is pi over 2 in the domain of this function? To know that, we have to substitute pi over 2 into sine of t first, because sine of t is inside ln. So if you substitute pi over 2 into sine of t, you find that you get 1. Okay, now ln of 1 is 0. So this function is defined at power 2. So therefore, it's continuous there at power 2, because this function is continuous in its domain, and power 2 is an element of its domain. So therefore, to find the limit of this function, you simply just substitute. You go ln of sine of power 2, okay, like this, which is basically equal ln. It's equal to ln of 1, because sine of power 2 is 1. Okay, so it's equal to ln of 1, and ln of 1 is 0. So in this case, the limit is equal to 0. And that's how it goes, guys, for continuous functions. That's how it goes for continuous functions. To find the limit of a continuous function, you simply just substitute. But you have to know, is it continuous or is it not? Okay, you have to know that is it, and of course, these functions that are continuous in their domains. So you have to know, first of all, is the number that the variable is approaching, is it part of the domain of the function? First of all, if it's part of the domain of the function, and these functions are a part of the list of functions that are continuous in their domains, therefore, you can then substitute to find the limit. All right. So that's the examples we have there. Okay, we don't have to do another example. That's enough examples. So you guys, I'm sure you get the picture. I'm sure you get the idea of what's going on here. So now what I want to look at now, I want to look at this function here. Let's look at another example. Okay, I'm going to write example, and I'm going to write a function down, and I want us to look at this function here and see what happens with this particular function. So with this particular function, suppose that you have this. Suppose you have to find the limit of the following function. You have to find the limit of x squared. You have to find the limit of x squared multiplied by sine. So you see, it's a combination again, because you got a polynomial function, which is x squared. You've got a sine function, which is a trig function. Both of these functions individually, the polynomial function and the sine function, both of them, they are continuous individually. They are continuous in their domains, but their combination of them, in this case, is a combination where you multiply them. Okay, you multiply them. Now it's a combination of them, and also if this combination of them is defined, okay, if it's defined at the number that the x values are approaching, then it's also continuous at that number. So, but is it defined? Okay, so the function we have basically is x squared multiplied by sine of 1 over x. Okay, so it's x squared times sine of 1 over x, and we are finding the limit of this function as the x values are approaching 0. Okay, what is the limit of this function when x values are approaching 0? So that's what we're doing here. This function is also, because it's a combination of the functions in that list of continuous functions, this function here is also continuous in its domain. But the thing is, the question is now, is 0 part of its domain? Meaning that is 0 an element of its domain? Meaning that is the function defined at 0? Is this function defined at 0? If we take 0 and we substitute it here in this function, we will get 0 squared multiplied by sine of 1 over 0. That's what we get when we substitute 0 into this function here. Now, what do we get though? What does that give? What does this give? You got sine of 1 over 0. But then we can't divide by 0. Division by 0 is not defined. So your calculator will give you an error to indicate this, meaning that this function that we have here is not defined at 0. So therefore, 0 is not in its domain. Therefore, this function is not continuous at 0. So therefore, you cannot use continuity to evaluate the limit of this function. Okay? Now, to evaluate this limit, since we can't use continuity, since we can't just simply substitute, there is a way of evaluating it, either than the table, and it's called the squeeze theorem. Okay, it's called the squeeze theorem. All right. Now, let's discuss the squeeze theorem. What is the squeeze theorem? There is a way of evaluating this function, of evaluating the limit of the function, and this way is called the squeeze theorem. But the question is, what is the squeeze theorem? That's the question. The question is, what is the squeeze theorem? What is the squeeze theorem? So let's discuss then what the squeeze theorem is. Okay. Now, what I'm going to do first, I'm going to state the squeeze theorem. I'm going to state it. I'm going to state it. Okay. So I'm going to say this. Suppose the following. Okay. Okay, so guys, as I was saying, let's then discuss the squeeze theorem. So suppose that f of x, so f of x is a function. Suppose that f of x is always bigger or equal to another function. And suppose that this function is g of x. And at the same time, suppose that this f of x is always less or equal to another function, which is called h of x. So basically, this function is squeezed in between these two functions. And suppose that this is so for all x values in some interval. So this is so, this is so for all x's element of some interval, meaning that for all x's belonging to some interval I. Okay. And also suppose that there's a number a, which is also part of this interval. suppose that A is also part of this interval I. So that's the things that we suppose. Okay, we suppose that a function f of x is between two functions, which is g of x and h of x, for all x's in some interval I. Meaning that for any number in this interval I, the function f of x is always squeezed in between these two functions, g of x and h of x. And also, there's a number a, which is also inside this interval. Okay, so suppose that's the case. Now, now we say this. Now, in this case, we say if the limit of the function g of x, okay, so if the limit of g of x, which is this function to the left of f of x, if the limit of g of x, when x approaches a, is equal to all right. So now this is what we suppose. So suppose that f of x is between this g of x and h of x. First of all, for all numbers inside this interval I. Okay, and also suppose that a is also part of this interval I. Now I'm saying this. Now I'm saying if the limit of this function g of x, which is the function to the left of x, if the limit of g of x when x approaches this number a, if it's equal to the limit of h of x when x approaches the same number a, okay, then if it's equal to another number, let's say L, okay, we say then the limit of the function f of x, which is the function in between these two functions, when x approaches a, is also equal to L. So that's what the squeeze theorem says. If the limit of g of x when x approaches a is the same as the limit of h of x when x approaches a, is equal to some number L. Suppose it's just equal to L. L stands for a general number. Okay. If the limit of g of x when x approaches a is equal to the limit of h of x when x approaches a is equal to a number L, then the limit of f of x when x approaches a is also equal to the same number L. That's basically what the squeeze theorem is saying. It's saying that if the functions to the left and to the right of this function that's squeezed in between, if they follow the same limit, then the number in between, the function in between, also follows the same limit. Okay, right? That's what it's saying. If these two functions to the left and to the right of f of x, if they have if they approach a certain limit, if they both approach the same limit, then also the number in the middle also approaches the same limit. Then. So that's what the squeeze theorem is saying. Okay, guys. So as I was saying, that's basically what the squeeze theorem states. Okay. Suppose that a function f of x is squeezed in between two functions. To the left, you've got g of x. To the right, you've got h of x. Okay. If the limit of the function to the left is the same as the limit of the function to the right, then the function in the middle also has the same limit. That's basically what it says. All right, that's what it says. So how do we then use this theorem to calculate or to evaluate the limit of this function here? How do we do that? It's simple. Let's do that. Let's use the squeeze theorem to evaluate this limit here. Okay, let's use the squeeze theorem. Let's use the squeeze theorem to evaluate this limit here. Let's use the squeeze theorem. Okay, so to start, let's start with the sine function. Okay, sine of 1 over x. We start with the sine function. And what do we know about the sine function? We know that the sine function is always, it doesn't matter what you put in here, in the domain of the sine function. Sine of, it doesn't matter what you put in here. If you substitute the number in here, of course, it must be defined at that number. That number can't be 0. So if you substitute any number in here, you'll find that the sine function is always between -1 and 1. Okay, it oscillates between -1 and 1. All right, so we start there. We start with that inequality. And then we multiply throughout the inequality, we multiply x squared, because we want to have x squared times sine of 1 over x in the middle. Okay, so multiply throughout this inequality, the number x squared, and we get minus x squared. To the left, and in the middle, we get x squared multiplied by sine of 1 over x. To the right, we get x squared. So that's what we get. So we basically just form this inequality that we can use to evaluate the limit of this function in the middle using the squeeze theorem. So how then do we use the squeeze theorem in this case? It's simple, because we can see now we've got an inequality. We've got a function to the left and a function to the right. So what we want to know now is, what is the limit of the function to the left? The function to the left is minus x squared. So what's the limit of minus x squared as x approaches 0? What is the limit of minus x squared as x approaches 0? What is the limit of minus x squared as x approaches 0? Okay, let me erase this. Okay, minus x squared. What is the limit of the function on the left, to the left, which is the function minus x squared? What's the limit of minus x squared as x approaches 0? Well, this minus x squared is defined at 0. Therefore, it's continuous there. So therefore, we can just substitute to get the limit, and that gives us a 0. So the function, it approaches 0. The limit of this function to the left is 0. What about the limit of the function to the right? What about the limit of the function to the right? You'll find that it's also 0. Okay, you'll find that it's also 0. If you find the limit of x squared when x approaches 0, now it's positive x squared now. Again, you just substitute the 0 in there, and you get 0. So it's 0 squared, which is equal to 0. So you can see that the function on the left and the function on the right, they have the same limit, and it's 0. The function on the left and the function on the right have the same limit, and that limit is 0. Okay? The function to the left and the function to the right have the same limit, and this limit is 0. So by the squeeze theorem, we say therefore, okay, we say therefore, by the squeeze theorem, okay, by the squeeze theorem, the limit of the function in the middle, which is of course the function x squared multiplied by sine of 1 over x when x approaches 0, is also equal to 0. Okay, so that's how you this is how you apply the squeeze theorem. This is how you apply the squeeze theorem. As simple as that. This is how you apply the squeeze theorem. As simple as that. The limit of the function to the left, which is minus x squared, when x approaches 0, is 0. Also, the limit of the function to the right, which is x squared, when x approaches 0, is also equal to 0. So therefore, the function on the left and the function on the right approach the same thing, meaning that the function in the middle also approaches that same thing too by the squeeze theorem. So that's how you apply the squeeze theorem. You apply it in this way. It's very simple. So guys, we're going to end there. I'm going to give you guys a tutorial to revise this. I'm going to post this lecture. We're going to stop there. So I'm going to post this I'm going to post this lecture. I'll post it online on Blackboard. And I'm going to post another lecture on derivatives immediately after that. So you guys have to go through these lectures. You have to watch these lectures. Watch this lecture and also watch the lecture on derivatives. Watch this lecture and also watch the lecture on derivatives. And the lecture on derivatives is the last lecture of the term. And yeah, okay, let's stop there.